So I'm going to present this work, which is joint work with my colleagues Sushmita, Azad, Max Fowler, Matthew West, and Craig Zilles. Craig is going to answer questions. So if you guys have any questions, please enter it in chat. Here by assessments, what we mean is summative assessments, speaking of which the need of proctoring is usually taken as granted, regardless of the format of proctoring. But we know that proctoring is kind of expensive. What if we don't proctor? Well, there is mixed result in the literature, although largely in support of the need of proctoring. So in this work, we studied an introductory program course for non-tech majors in one of the semesters before the COVID, and we have around 510 students. There are 5 proctored exams and 4 unproctored exams. Each of the students has taken all of these 9 exams. This is what we mean by within subject design. So there are 3 main findings. The first finding is that we found students scored 3.32 percentage points higher in unproctored exams. We refer this as unproctored advantage. So 3 percentage points doesn't sound a lot, but that's 1/3 of letter grade. More interesting, we found that this unproctored advantage increased from around 0 to around 7 percentage points throughout the semester, as illustrated in this figure, which I'm going to introduce how we obtain this figure. So, and we have some evidence suggesting that this is due to students learning to cheat throughout the semester. And the third finding is that certain type of questions had higher unproctored advantage, although we don't know what the causes of this phenomenon yet. Okay, so speaking of proctored and unproctored exams, let me introduce the settings. So there are similarities and differences between them. So the first similarity is they are using the same platform, which is parallel. The second similarity is that they are both asynchronous. So in the proctored exam settings, students have time slots that they can choose from, usually in a 3-day time window, whereas in unproctored exams, students can choose whatever time they want before the deadline. The major difference between them is, of course, the exam environment. In proctored exams, we have students will have to go to what's called computer-based testing facility, which is the figure shown below. Essentially, it's a room with a lot of computers with dedicated proctors and security measures that tries to prevent cheating. Whereas for unproctored exams, they can take anywhere that they want on Earth. The other difference is honor code. So this is from a university without honor code. So we don't ask students to pledge honor code in proctored exams. But as in unproctored exams, as we want to make sure that students understand that cheating is not allowed, they have to pledge honor code before every unproctored exam. There are other information that are not hard to show in the table, which is exam schedule and their weights. So typically, the unproctored exams are worth 2 percentage points of the entire course rate, whereas a typical proctored exam is worth 10 percentage points. So one way we could study the proctored exams versus unproctored exams is that we can ask students a set of questions, let's say on U1, and we can ask them the same set of questions, let's say on P1, and then we can compare their performance. But the issue is, because students are being exposed to these questions in U1, there's this exposure effect that might influence how we interpret the result. So in order to minimize the exposure effect, fortunately, in our data set, we have a level of exam randomization. So for each exam, there are slots of questions. So in this particular exam, there's let's say 6 slots. And for each of the slot, there's a pool of questions where, let's say in pool 4, there are 6 questions, and each student will get a random draw of these 6 questions. And of course, we have larger pools, which has, let's say, 15 questions in the 20th pool of one of the exams. So in addition to this exam randomization, most of these questions themselves are randomly parameterized. So let me summarize the data we have. We have around 500 students, 5 proctored exams and 4 unproctored exams. We have around 128,000 observations in the format of student exam question score, meaning that a particular student have answered a particular question on a particular exam with a particular score. Here, score is a real number between 0 and 1 because partial credits is there. So in total, we have 347 questions, and 245 are shared between the proctored and unproctored exams, meaning that they appear in at least one of the proctored exams and at least one of the unproctored exams. So this sharing of questions between these two types of exams is what allowed us to carry out the following study. So we're going to fit a logistic model. Let me walk you to trying to study the unproctored advantage. So let me walk you through this model. So here Z is the score of an observation. Sigma is the sigmoid function. SI is the 0-1 indicator of student I. If SI is 1, meaning that this observation is associated with student I. And alpha I, we can interpret this as student I's ability. QJ is a 0-1 indicator of question J. Again, if QJ is exactly one of these indicators will be 1, and if it is 1, meaning that this observation is associated with question J. Beta J, we can interpret this as question J's difficulty. And mu is a 0-1 indicator of unproctored exams. And gamma here is the coefficient that we care about, which is unproctored advantage. So here I'm listing all the observed values in the top and model coefficients in the bottom. So this is essentially a modified version of the most basic IRT model. So if we fit this model on our data, we'll get gamma equal to 0.28. While this is a coefficient in the logistic model, it's not readily interpretable. So what we do is going to convert this coefficient into percentage points as follows. So we're going to ask the model, once we fit the model, to predict what the student is going to get on, student I is going to get on question J in unproctored settings, which we denote as Z hat IJ1. And again, we're going to ask the model to predict what student I is going to get on question J in proctored settings, we denote as 0 IJ0, so Z hat IJ0. And the difference between them is the unproctored advantage on that of student I on that particular question. And if we average this over all the questions, we'll get CI, which is student I's unproctored advantage. So if we plot the distribution of CIs, this is the figure we'll get. This is a histogram of the unproctored advantage in terms of percentage points. So as the mean is somewhere around the red line, so which is 3.32% points. This is not surprising given that the literature supports that there's a need for the proctoring. Okay. What's more interesting is that when we take into account of the time effect. So here, the left part of the model is exactly the same as before. In the right, instead of having just a single indicator for unproctored exams, we have a product of the 0-1 indicator of student I and the 0-1 indicator of unproctored exam L. So we're separating out the individual exams and individual students. And here, delta IL, we can interpret this as student I's unproctored advantage on unproctored exam L. So if we fit this model and then do the percentage points conversion again, we'll get this list of histograms. So here I'm plotting the unproctored advantage for each exam. And as we can see, for unproctored exam 1, the unproctored advantage, sorry, for unproctored exam 1, the advantage is kind of centers around 0. Whereas time goes by, there's clear trend of shifting to the right. And if we compute the mean of these distributions, this is the figure that we'll get, which is the figure that I've shown at the beginning of the presentation. So here on the y-axis, I'm showing the mean unproctored advantage in terms of percentage points. And the x-axis, I'm showing the different unproctored exams. So it is pretty clear that at the beginning of the semester, the unproctored advantage is closer to 0, but as time goes by, it reaches to 7 percentage points. So we think that this is due to students learning to cheat here, and here is the evidence that's suggesting that. So here, I'm plotting the amount of study that students have shown before each of the exams. So before each of the unproctored or proctored exams, we actually offer students a practice exam generator that students can request as many practice exams as they want. And so here on the y-axis is the number of submissions made by students normalized by the number of questions in each of these practice exams. And as we can see, the amount of studying for unproctored exams is decreasing over time. Whereas there's no clear trend for proctored exams, but if one has to say anything, it's kind of slightly increased a little bit. So we take this as evidence that this increasing in unproctored advantage over time is really due to students learning to cheat. Okay. We also studied on how these unproctored advantage correlates to question types. So here is another model where the life card is again essentially the same as before. On the right, instead of a product student indicator, which is the unproctored exam L, we have a 0-1 indicator for question types and then unproctored exam L. So epsilon KL, we can interpret this as unproctored advantage of question type K on unproctored exam L. And so if we fit the model, this is the result we get. So I'm plotting the mean unproctored advantage in terms of percentage points for all exams grouped by the question types. So as we can see, again, there's still this increasing in unproctored advantage over time. But what stands out is that programming questions had way larger unproctored advantage as compared to other type of questions. So here on the right, I'm showing the features of these questions. So for programming questions, on average, had the highest difficulty, and each individual of these questions had highest weight, and also has the lowest amount of randomization. But we don't know which features or which combination of features has caused this phenomenon, which this requires feature research. Okay, so the main takeaway for this study is that proctoring is important for summative assessments. And repeated exposure to low security environments basically invites students to cheat. So if one wants to have a unproctored high-stake summative assessments, then there should be only one of them. Otherwise, students are essentially forced to case the joint. And the last takeaway is that studying the effectiveness of security measures over time is important. Knowing that a security measure works at the beginning of the semester doesn't mean that it's going to work as well in the later semester or throughout the years. Maybe security measure is not as useful as it was. Of course, there are a few limitations of this work, but for the time interest, I'll just leave it there. And I'm happy to take any questions.
Fantastic. Thank you, Binglin. Very useful to know, especially at this time, as others have pointed out in the chat. You do in fact have 2 minutes. So if there's somebody who would like to ask a question, raise your hand. Or Binglin, feel free to pick one out in the chat. Oh, Jack has one.
We've been discussing this in the chat. If you can disaggregate the programming questions by which ones were randomized and which ones were not, you'd have even stronger evidence of cheating. Is that feasible?
Well, I think all the programming questions are probably not randomized because, again, so I think the way randomization works in STEMs is because we are asking students to apply some kind of algorithm, but programming questions, we are asking students to write the algorithm itself. And so I think most of the programming questions are not randomized. The only randomization is that they are selecting from a pool of questions. So I'm not sure if that answers the question.
Well, you could design some parameters into them, but I understand what you're saying. I used to address this when I taught intro computer science by having students like output some function of their name, something where different students would have to provide different answers. But that was an elementary course.
Great. Thank you, Jack. Thank you for the answer. Again, thank you, Binglin, and thank you for all the speakers in this fantastic last session of the conference.